Okay, this is chapter 5, where we are focusing primarily on the structure of the atom. We already know that the atom has a structure made of three basic particles: protons, neutrons, and electrons. And we didn't just magically know that. This idea of an atom came along way back in 400 BC, first used by Democritus. And what he meant by the word atom was that it was a single indivisible part. In 1800, approximately, Dalton, who was an English teacher, actually came up with four postulates to help explain what an atom was. First, said that all elements are made of indivisible particles, which are called atoms. Then he said that atoms of the same element are alike with each other, but they're different from atoms of another element. So we get this idea of categorizing atoms into types. He said that reactions would rearrange the atoms, but couldn't create or destroy them, and we call that conservation of matter today. He also came up with this idea of compounds, and he said that a compound would be made when you're combining whole atoms. In 1897, J.J. Thomson actually is the person who discovered the electron. So up until that, we were thinking of atoms as these single, whole, ball-like particles. When J.J. Thomson used a cathode ray tube, what he did was he was heating different elements, and when he found that when he heated them hot enough, these elements would release rays that were attracted to a positive charge. And so he decided that, well, these rays, since the elements are releasing them and they're attracted to a positive charge, they must be negatively charged, since we already knew at that point that opposite charge is attracted. And since all heated elements were found to release cathode rays, he discovered that every element, every atom has to have some kind of negatively charged particles as part of them. And so that was the first discovery of the electron. Rutherford came very shortly after J.J. Thomson. In fact, Rutherford had worked for J.J. Thomson, and he came up with this experiment called the gold foil experiment. And what he did was he shot alpha particles, which at the time they didn't know what they were, so they called them alpha particles, but we now know that they're helium nuclei. So it was two protons and two neutrons all stuck together to make like this particle called an alpha particle, and that was shot at a piece of gold foil. Very, very thin gold foil. And what was found that most of these alpha particles went straight through. And so in that way, they were able to determine that the atoms are made of mostly empty space. He did find that a few of them were deflected to the side, which said, well, there's got to be something solid in there. And every now and then, one would bounce straight backwards. And so because the helium nuclei are positively charged, and because these solid, dense parts of the gold foil were repelling them, we found that there is a nucleus and it's positively charged. So a lot of really good ideas about atomic structure came from Rutherford. We found out that the atom was mostly empty space. We found out that these positively charged particles had to be repelled, and so we knew the nucleus had to be positively charged. And we also knew that there was something with significant mass that was bouncing back these alpha particles. And so that told us that the mass of an atom was concentrated in one dense center area, which we now call a nucleus. So there are three very important ideas to take away from understanding the interior of an atom. We know that atoms are made of neutrons, protons, and electrons. So atoms themselves are not indivisible. They are made of smaller parts. We also know that the number of protons and electrons are equal if we have a neutral atom. The number of protons will determine the type of element we have, and most properties of an atom are determined by its electrons, since atoms will interact with each other by their electrons. The nucleus is so dense in the center that two nuclei of atoms will rarely come close together. It's the electron clouds that will overlap, and so those electrons will actually interact with each other. Again, the nucleus is very small compared to the rest of the atom, and it contains almost all of an atom's mass, with the protons and neutrons concentrated there. We already have discussed that protons and neutrons have much more mass than electrons, and since the protons and neutrons are in the nucleus, then it follows that almost all of the mass of an atom is concentrated in that nucleus. The atomic number is simply the number of protons of an atom, and it's what determines the type of element we have. Atomic mass is the number of protons plus the number of neutrons. Now, an isotope is a word we use to describe elements that can have varying numbers of neutrons. So the number of protons cannot change without changing what element we have. So we know that the number of protons stays the same, but the number of neutrons will change. So carbon-12 has a mass of 12, and since it has 6 protons, we know it has to have 6 neutrons. Carbon-13 has a mass of 13, and again, it has to have 6 protons in order to be considered carbon. So that means the rest of the mass, the 7, must come from the neutrons. And likewise, so would follow that carbon-14 has 6 protons still, but then 8 neutrons. Carbon-12, carbon-13, and carbon-14 are 3 isotopes of carbon. The electron cloud houses the electrons, and electrons have, again, much less mass than protons and neutrons, and they are way faster moving. So protons and neutrons just kind of sit in that nucleus, not doing very much, but the electrons are constantly moving around in that cloud. And we call the area a cloud simply because the electrons don't travel in orbits. A cloud is just an area where we're likely to find them. Okay, protons, again, reviewing, have a positive charge. Neutrons have no charge at all. They're neutral. And electrons have a negative charge. We know that charges exert an electrostatic force. You've got to be able to recognize that the word electrostatic has to do with charges. Like charges repel and opposite charges attract. And neutrons don't feel any electromagnetic force at all because, again, they are neutral. An ion is simply an atom that has lost or gained electrons, okay? It's not going to gain or lose neutrons very easily. That's called nuclear chemistry, and that should make you think of like lots of energy having to be placed in to tear apart that atom. So it's just the electrons that are easy to change, okay? And if an atom gains or loses electrons, it causes a charge unbalance, okay? A charge imbalance. The total charge becomes unbalanced. The number of protons then does not equal the number of electrons. And so because the pluses and the negatives don't even out, we end up with this overall charge on the atom. We call that an ion. Cations are elements that have lost electrons. So because they're losing negative charge, they become an overall positively charged ion. Anions, on the other hand, are elements that have gained electrons. So because they're gaining more negative charge, it gives them an overall negative charge on the ion. For example, sodium really would like to get rid of an electron. And when it does that, it loses one negative, so it has a proton that's not being canceled out. So a sodium ion would be a cation with a +1 charge. Oxygen, however, wants to gain 2 electrons. And so because it gets 2 extra negative charges that aren't canceled out by any protons, it has an overall -2 charge on its anion form. So we get to this idea of, well, how come we have atoms that are gaining and losing electrons? And when we're trying to figure that out, we have to then look at electron configuration, okay? According to quantum atomic theory, all atoms want to have the same electron configurations as noble gases. And that should prompt a question from you saying, well, why is that? And the reason is noble gas electron configuration is very stable. Remember, everything seeks stability. And then we might ask, well, why is it stable? And so we use quantum theory to help answer these questions. First of all, electrons are not solid, but they act more like waves. And wave properties will force electrons into a pattern that minimizes their energy. So remember, everything is looking for that lowest energy state so that it can be stable. And the wave properties will force electrons into a pattern that is stable and has that lowest energy level. Each unique place in this particular pattern is called a quantum state, and each quantum state can hold a single electron. Electrons are always found in one quantum state or other, but they are never found in between states. So it can't exist in between. It's either in one state or it'll jump to another state, but it's not going to be halfway there. Also, another rule of quantum theory says no two electrons can be in the same state at the same time. Electrons can switch places, but they can't both be in the exact same state. So now we're starting to think of electrons as waves instead of particles. And, we're used to thinking of electrons as these balls, maybe like the small blue balls that you had played with in class using the models. Now we're going to start to think of them as these particles. And it helps us understand why electrons could be occupying part of a cloud instead of like this orbit. Okay, and so it spreads the mass and position of these electrons out over space. And so if we think of electrons as waves, we need to understand what properties waves have so we can help explain how electrons behave. Remember that waves transport energy. It's their sole purpose. And waves have frequency. They also have wavelength. Frequency tells us how fast a wave is hitting a particular point, and wavelength determines how much energy a wave can carry. Higher wavelengths mean lower energy, and lower wavelengths mean higher energy. So again, frequency is the rate at which your wave is moving. Wavelength is just the distance between peaks or valleys. So again, only certain energies are allowed in a particular atom, and we call those quantum states, and those specific allowed energies are quantized. So what does the word quantized mean? Well, quantized should make you think of quantity, specific amounts, okay? No halfway in between. It's either in one state or another. You can't partly be there. And if you look at the diagram, you can see these whole states are allowed, these whole wavelengths, or 1.5 wavelengths, but not just parts of wavelengths. So electrons inside atoms can only have specific energies that match the exact wavelengths that they're allowed to have. And that's how we get to this idea of quantization, because only certain wavelengths are allowed, only certain quantities of energy are allowed. So now we're going to bridge into this idea of orbitals. Electrons do not travel in orbits or circular paths. They're in these areas or clouds where we're likely to find them, and we call these areas orbitals. I know orbit sounds like orbitals, but they have nothing to do with each other. They're not alike in any way. An orbital is corresponding to an energy level that an electron has. And the shapes of orbitals can be really funky weird. They're not just these round spherical shapes that we normally think of. So it's time to really start to move away from this idea of circular orbits and into this new idea that, well, there's a range of areas that we can possibly find electrons in, and the shapes will vary depending on the energy levels, which is really cool. And we're going to spend time in class working on these ideas. Okay, I'm going to fast forward through all this because I'm going to have to read a separate explanation of all these in order to stay underneath the 15